Okay, awesome. Good morning, everyone. Let's get started. So today I have a couple things which relate to telescopes with multiple antennas, radio telescopes with multiple antenna studies. I'll be covering the beamforming directory, and you can see in here there are two GNU radio flow graphs. We will first be doing this beamforming demo and next the beamformer array demo. And the reason why we are doing this session today is because next week we will be on a field trip to the Allen Telescope Array. As you will see, it's an array with 42 antennas. So the goal today is to understand with some demonstrations why it is useful to have multiple antenna receivers in radio astronomy. And that being said, let me get started. So I have my radio companion here. And what I'm going to do is I'm going to make this beamforming demo from scratch to explain step by step how it works. But I will keep this on one side to copy, for example, some of these Qt GUI entries so that I don't have to type exactly all the labels and everything.
Sorry, Daniel. Can everybody see this from the back, or do we want to zoom in just a little bit?
We zoom in. Yeah.
Oh, okay, yeah. Definitely, I should zoom in. I think this size is the right one, right? Yeah, thanks for the reminder. So let me take a look at what's the sample rate I have. Okay, 1 mega sample per second. So I'm going to save this as beamforming demo 2. And basically the thing I want to simulate in here is we have an astronomical source and we have a receiver, which is a telescope with 2 antennas. So I'm going to simulate 2 receivers. And the goal here is to do beamforming, that is to combine the signals from the 2 receivers to increase the signal to noise ratio. And we will see exactly how that works. So for the simulation of the astronomical source, the thing I'm going to do is essentially the same thing we were doing last week. I'm going to use a signal source, a noise source, a Gaussian noise source for the astronomical source, because in many cases, astronomical sources generate broadband noise. So here what we are going to do is to generate band limited noise, that is noise which only occupies a portion of the spectrum, so that it is actually easy to see the signal to noise ratio. We will be able to see like the source is in some part of the spectrum and then the rest of the spectrum is the noise floor. So that's a goal, and just as a reminder of how we did that last time, we have this noise source, which is a Gaussian. Then we have a polyphase arbitrary resampler to change the sampling rate so that this is not white anymore, so that this doesn't occupy the whole spectrum, but only a portion of it. And if we want to shift this in frequency to place it in a particular location of the spectrum, we had a signal source and a multiply block, multiply, that's how it's called. And we saw that by multiplying any kind of signal with a complex exponential, which is created by the signal source set to cosine, and complex type, which is the blue color, we achieve frequency shift of this input signal here. So that's what my astronomical source signal is going to be. And I should adjust some of the parameters. Let me see if I have in here I'm going to copy all of these entries because they are going to be useful later on. and maybe also this variable. And I will go one by one as we are using them. So wideband bandwidth is the bandwidth of the source in kilohertz. So I have set that to 100 kilohertz. We have 1,000 kilohertz of total bandwidth. So this is occupying just 10% of the bandwidth. And then the resampling rate is basically the formula we learned last week. So that's our total sample rate divided by our wideband bandwidth. But because the sample rate is in samples per second and this one is in kilohertz, we need to multiply by 1,000. So 1,000 times the wideband bandwidth. And this should be 10. And if I hover and if I didn't make any typos, it seems, no, that's okay. If I hover on the field, we can see that the value is 10. And that makes sense because the noise source is going to be 10 times narrower than the whole bandwidth we have. So that's 100 kilohertz compared to 1 megahertz. And that's all we need here. Then something else. So for the Gaussian noise, again, it's the same formula as before. So we need a square root because we are converting power basically to amplitude, and amplitude is the square root of power. Then the wideband SNR. So I have it here. I have this Qt GUI entry, wideband SNR, and that is the signal to noise ratio. And last week we were using CN0 in units of decibels per hertz. So that is how much power does our signal have versus how much power does the noise floor have in 1 hertz. Here I'm going to use something slightly simpler, which is more convenient for this simulation, which is the SNR of the whole noise source compared to the noise floor in the bandwidth occupied by the noise source. So how should we think about that? We have the noise source. It's occupying a bandwidth of 100 kilohertz. And then the noise floor will be spread across the whole spectrum, so 1 megahertz. But if we look at just the noise floor, which is in the same bandwidth as our signal source, then we can measure its power. And the SNR we are using, so the definition for SNR we are using today is basically the power of this noise source divided by the power of this other noise floor in 100 kilohertz. That will be much easier to understand when I run this, and we can see it on the spectrogram, and we will understand why I'm making this choice for the definition of the SNR. So then this is the SNR. I'm converting from decibels to linear units of power. And the other thing I need to do is to divide by the noise power. So that's, I have here, I'm actually copying from the flow graph I have already prepared to avoid mistakes. So let me copy, and then we can think about why we have this formula. Let's see, I'm missing some parentheses. How many do I need?
You need to import NumPy.
Sorry?
You need to import NumPy so that NP is not defined.
Oh, yeah. Good point. I need to import NumPy. So I can import NumPy the same as the other week. Import NumPy as NP, and then we get our number. So let me see if I can make this thing larger. Yeah, and we can see the whole formula. So then, what's the reason for this? Basically, something that we will do is we will use power of 1 on the noise floor of each receiver, and that's the power across all the bandwidth, so across the 1 megahertz bandwidth. But then the question is how much, what is the portion of that bandwidth which is occupied by this noise source, and that's only 1/10. So I have that here. Basically, I have my sample rate, that's 1 megahertz, divided by the wideband bandwidth, converted from kilohertz to hertz. So this is 100,000. And then this whole fraction is 10. So what I'm saying is I should divide this quantity by 10 because my signal to noise ratio is defined as the power of this noise source divided by the power of 1/10 of my noise floor, because it's my noise floor only in this 100 kilohertz bandwidth. So that's how this works out to be. We could rearrange this also, and this thing which is like twice on the denominator, we could put it multiplying on top. But that's what we want. And then let me put really quickly a frequency GUI sync and show you why I have used this definition of SNR. And maybe I want some kind of average, so I can turn this here, maybe medium. And yes, what I'm missing is the noise floor. And this will come afterwards. We are going to use a new block to simulate not only the noise on receivers, but also other effects such as Doppler. But at the moment, what I'm going to do for the sake of the explanation is to add a new noise source, which has a amplitude of 1. So that means the noise power will be 1 to get essentially the thing I wanted to show here, which is this. And now what's happening is the signal to noise ratio is defined as 0 decibels. Let me put more averaging even. So that means the power of this noise source, which is going to represent our signal of interest, so our astronomical source, is the same power. So 0 decibels means the same power as the power of the noise floor in this part of the spectrum. So what happens when I combine the two noise signals with this add block is that because they are uncorrelated, and I will get to that again in a moment, the powers sum. The power we get here is the power from here plus the power from here. So then if the two powers are equal in this part of the spectrum, we get basically twice the power. And twice the power is an increase of 3 decibels. And do we get something like that? We should. So the noise floor is at about minus 44.5, I would say. And this should be minus 41.5, and it is. So that's what makes it very easy to understand what's going to be the noise, the power of this noise in comparison with the power of this noise floor, even if we change the bandwidth. So if I now make this 200 kilohertz, we can see that the power of this thing is now larger because it's occupying a larger bandwidth, but with respect to the noise floor in its occupied bandwidth, it's the same. It's also the same powers of the noise, so when I combine them, I get a 3 dB increase. And the same happens if I go to 400. If I go to 10, you can see it actually jumps up because I have two variables which depend on the bandwidth, and they are not updated exactly at the same time. So that's the reason. But once everything settles, it's also 3 dB above. So that's the reason why I prefer just signal to noise ratio in this demo, because it's like a measurement of signal to noise, which is relative to the occupied bandwidth. And so we get like the same behavior no matter what bandwidth we're setting here. Whereas if I were to use CN0 as in the previous week, then I would need to change the signal to noise ratio whenever I change the bandwidth if I still want to get like this 3 dB increase, which is good to see that there's something here which is present, but it's not too strong, and we can see it's there, but that's it. So that's the main purpose. Any questions so far? Okay, now we need to think about, we have this signal, like the one in here, basically the one we had before. If I delete this, and this is radio frequency energy, which is coming from some place in the sky. We have antennas on the ground, 2 antennas in this case we are going to simulate. And then the question is, what are the effects, the physical effects that we need to simulate? What things happen to this signal as it is arriving to the receivers? And one of the effects we already know, the receivers have a noise floor. That's both noise from the environment, so it can be a part of the contribution to that noise is the cosmic microwave background, which is always, no matter where you point in the sky, you will see the microwave background. It can also be, depending on the frequency and depending on the characteristics of the antenna, it can be galactic noise, it can be ground noise, it can be human-made radio frequency interference. So there are many contributors of noise which are like external to the receiver, but we also have the receiver. The electronics inside the receiver generate some noise, basically because of quantum effects. Since things are not at 0 Kelvin, then any resistor is going to generate noise. So, okay, receivers have noise. Then what else? There is a time of arrival to the receivers, because let's imagine some concrete situation to make this clearer. Let's think about 2 antennas on the ground. One is to the east and the other one is to the west. This is known as an east-west baseline. Basically, the line segment which joins the antennas is oriented east-west. And then we can think about the position of our source on the sky. Maybe it's on the eastern part of the sky. And as we think about the signal, which is arriving from that direction on the sky, it is going to arrive first to the receiver, which is to the antenna, which is on the east, because it is closer to the eastern part of the sky. And it is going to arrive just a little bit later to the receiver, which is on the western part of the ground. This is just because our signals travel at the speed of light. So whatever distance is between the 2 receivers, assuming, for example, that the source is exactly due east and also at 0 elevation, so that it comes like following the line of sight, then the time difference of arrival between the 2 receivers will be exactly the distance between the 2 antennas divided by the speed of light. And in any other geometrical combination, we can basically make a drawing of how is the geometry, and we can calculate what's the difference in travel path, which causes a difference in time of arrival. So the main message, the thing I want you to remember, is because the 2 antennas are not in the same position on the ground, the wave arrives to them at different times. You can also imagine the wave as a plane wave arriving from the source, and the plane wave doesn't hit the 2 antennas at the same time. Okay, so somehow we need to add this to our simulation. We need to delay the signal that is arriving to one of the receivers to simulate that it's arriving later. Then what else is happening? This delay is changing over time because the source moves on the sky, or apparently it moves on the sky. Actually, what happens is Earth is rotating. But from the point of view of an observer on Earth, what happens is the source is moving across the sky. And then what happens is if it rises on the east, initially it's going to be closer to the antenna which is on the east. Then the source will transit. It will be in the southern part of the sky, assuming we are in the northern hemisphere. And when it transits, it will be the same distance from the two antennas. So at this point, the difference of delays is 0. And then it will transition into the western part of the sky. It will be closer to the western antenna. And so the delay will be basically saying that the signal arrives first to the west antenna. So this delay is continuously changing over time. And the consequence is that the Doppler seen by the two antennas is different. Basically, um, one of the antennas will see a slightly higher frequency than the other one. And the reason why that happens is that because there is a carrier wave at the carrier frequency. So we could think we are doing our observation at 1 gigahertz carrier frequency. And then that has a carrier wave of 1 gigahertz, which has a wavelength of 30 centimeters, more or less. And this carrier wave is affected by the delay. It's also affected by the change of delay versus time. So that change of delay versus time is what causes a change of frequency or apparent change of frequency in the carrier wave, which we see as a Doppler shift in the signal. And then basically what I'm saying is because this delay is changing over time, the Doppler seen by each of the antennas is different. Another way of thinking about this is with respect to the phase. So you can think about this wave, which is 1 gigahertz. That means that every 30 centimeters, there is a repetition of the wave. And depending on where in that 30 centimeter part of the wave we are, we have one phase of the wave or another. We can measure the phase in degrees, for example, going from 0 to 360 degrees. And it's the same as with the delay because the wave doesn't arrive to the two antennas at the same time. The phase that the antennas are seeing is going to be different. They will be in different parts of these 30 centimeter periodic waves in general. And as the geometry changes, because the source on the sky is apparently moving, the relative phase difference between the antennas will change. And so we see a phase change over time. And a phase change over time is the same as a frequency. So we will see a frequency difference between the two antennas. I know this is like somewhat conceptual. We will see that in GNU Radio in a second. But before that, maybe any questions? If something I didn't say wasn't too clear, we can stop and explain again. Okay, then let's get to it. Let's get to trying to build a simulation of what I just described in GNU Radio. And for that, what I'm going to use is a block which is new for us. And this is called channel model. And the reason why it's called channel model is that in radio frequency communications, we usually call the channel every effect that happens to the RF signal when it travels from a transmitter to a receiver. So there's this channel model block, which is intended to simulate all of those effects. And you can see there are other more complex channel models, such as channel model 2 and dynamic channel model, because there can be more complex things that can happen to the signal. You can imagine, for example, if you are in a city, which is something that doesn't concern to us in radio astronomy, but it concerns to people who work on communications, for example, cellular communications. You have these radio frequency signals traveling across the city, and they are going to bounce off the buildings. They are going to diffract. So there are going to be very complicated effects as the RF signals travel through the city. And all of that is important because, for example, you might want to simulate what's the coverage area of a cell tower. So you need to have fairly complicated models. In our case, there is not that much between the transmitter and the receiver. There is the interstellar medium, there is the atmosphere, and we could think about how to model those. But for today, we will not be modeling any of those effects. The only effect we are actually going to be model is the fact that the receivers move with respect to the transmitter because the Earth is rotating. And that is quite important whenever we have an array of antennas. So what does this channel model do, and what are the parameters here? The first parameter is called noise voltage, and maybe this should be called noise amplitude. It's called voltage because sometimes people like to think in electrical terms or in terms of electronic circuits. So if we have a noise source in an electronic circuit, the amplitude would be the voltage. But this noise voltage is basically equivalent to the amplitude I have in here in the noise source. So I want to set this to 1. This is the thing that will define the noise source of the noise floor of my receiver. And I said we are going to normalize this at 1. Then we have the frequency offset. We will care later about the units, but this is how we can introduce a frequency shift, which is going to simulate the Doppler shift between the two receivers. What I'm going to do, because we are only interested in the frequency difference between the two receivers, is I'm going to leave this at 0, and then the second receiver will have some frequency offset. Then there is this parameter which is called epsilon, and I don't like this name at all because what does it mean? I guess it's like some mathematical term in some formula, and it's explained here actually, and the explanation is reasonable. So this says the sample timing offset to emulate the different rates between the sample clocks of the transmitter and receiver. 1.0 is no difference. The main reason or the main use case for this field is what it says on the documentation, to simulate that the sampling rates on the transmitter and receiver are slightly different because sampling rates are generated by a physical quartz oscillator, and they will never be exactly on frequency. So in communications, that is pretty important to simulate. For us, we are going to use it for something slightly different because this sampling frequency difference, the effect that it causes is a variable delay over time. It's a delay that increases over time. So when I said as the Earth is rotating, the delay that the antenna see will be changing continuously, that is the thing we are going to simulate with this epsilon. And 1.0 means no change. It's basically, this is like the quotient of the sample rates or the quotient of delays. So both delays are the same, like input delay and output delay are the same. That's what 1 means. On the second receiver, we will change this to a value which is slightly different from 1. And in that way, we will simulate this variable delay. Then we have taps, and we are going to use the taps for the phase difference. I should explain in more detail why this is called taps and why it's a vector. So the thing is that when you have something which is called multipath, which means that the radio frequency signal arrives to the receiver through multiple paths, because again, coming back to the example of radio frequency propagation on a city, there can be a direct line of sight path, which is the straight line between the transmitter and receiver, but then maybe the signal reflects off a building, and so there is another path which has one reflection, and there can be many other more complex paths involving multiple reflections. So all of these paths will contribute to what the receiver sees. You can think about them as echoes. If you are on an echoey room and you are talking, then you will hear your voice, but then afterwards you will hear like the echo, and if it's really echoey and large, you might hear like a second echo and so on. So you have all these echoes, and the same happens with radio frequency propagation. Um, all these echoes are received with a delay, and the way this delay is realized is with a filter. which has tabs which correspond to each of the delays. So that's called tapped delay line. And for example, I could do something like 0 and then maybe 0.5. And that means the first signal which is arriving has an amplitude of 0. Then with a delay of 1 sample, there is nothing arriving. With a delay of 2 samples, there is a copy of the signal. So that's an echo with an amplitude of 0.5 times the original amplitude. And I don't know, I could put a bunch more of zeros and then 0.1, saying with a delay of how much is that? 1, 2, 3, 4, 5, 6 samples. We have an echo of the signal whose amplitude is 10% of the original. So that's how this is normally meant to be used. It's just so that you can list all your rays. They are also called rays in some cases because it's like the RF array, which is following some path. You need to think about this in optical terms where people do ray tracing. And you put the rays in here, you put their amplitudes. We are not going to use it exactly like that because we are only going to simulate the direct signal, so this one. But the useful thing for us is this is a complex vector. So that means these numbers can also have faces. They can have an imaginary part because also with these rays, when there is multipath, they arrive to the receiver at different phases. So it's not that only the thing that changes is the amplitude. The thing that changes can also be the phase, and I could put here a phase difference. So this means that the phase of the signal is also shifted by 0.1 radians. So that is the thing we are going to use. We are going to use only like one complex number to simulate a phase difference between the two receivers. But for receiver number 1, I'm going to leave this as amplitude 1, phase 0, which is just the complex number 1.0, which means basically do no changes to the signal. These are the main parameters, but then there is also the seed. And the seed is to generate the noise because noise is random. So generating noise on the computer amounts to generating random numbers. And then if you think about it, the computer cannot really generate random numbers because generating a random number is like throwing a dice. And in the computer, everything is code and it's deterministic. So whenever we generate random numbers on the computer, they are technically pseudo-random, usually. They can rely on external factors which are unpredictable, such as, I don't know, network traffic, which the computer is seeing. But ultimately, there is like a deterministic algorithm. So if you've done any random number generation in Python, you are familiar with this. You need to initialize the random number generation with a seed, which can be the time, and then you get like non-repeatable simulations, or you can use a fixed number as the seed, and then you get repeatable simulations, and you can run your simulation again and again, and you will get the same result, even though you are generating random numbers as part of the simulation. So here's the same in GNU radio. Anything which is random has a seed. And because in here I'm going to be generating different noises, I will be using different seeds in all of them, because otherwise I will get the same numbers and things will not work as expected. So this channel model is going to get a seed of 1. And this is receiver number 1. I'm going to, I don't think I've showed this yet. So if you go to advanced, there is a field which says comment, and you can type anything in here, any text, and it will show in here. So it's a good way to document why there is a block in the flow graph, what it is doing, or how the parameters need to be set, or whatever you find useful. So these are going to be receiver 1 and receiver 2. And very importantly, because otherwise nothing of what we'll do will work, the noise on these two receivers is different. I want to use different seeds on the receivers because otherwise I would get exactly the same noise. And that doesn't represent what happens physically in the receivers because basically the noise is uncorrelated. The main contributor to noise is the electronics of the receiver. And if I have two separate receivers, the electronics are separate. and there is nothing in common between them. So we get independent or statistically independent and correlated noise. So that's the reason I have two seeds. Then the question now is how to set the noise voltage is already set to 1, but how to set the frequency offset, the epsilon, and the taps for the second receiver. And for this, we are going to use these entries that I copied from the flow graph. So we have a phase difference in degrees that represents the signal is arriving with different phases to the two antennas. We have a frequency difference. This is frequency difference in hertz. That means the signal is arriving with different Doppler shifts to the antennas. Or another way of saying it is the phase difference is changing over time. 1 hertz of frequency difference means that the phase difference changes 360 degrees every second. So this is like the derivative of this thing. Then we have delay difference. So how much delay difference is there between the two receivers? And this is going to be measured in samples. Remember, because we have a sample rate of 1 million samples per second, each of these samples is 1 microsecond. So you could convert from meters to seconds by dividing by the speed of light, and then you could convert to samples by multiplying by the sample rate if you are starting with your physical distance between the antennas. So we are also going to set this here. And then finally, there is the delay rate difference. So this is like the time derivative of this thing. And I want to have this in parts per million, which is a useful unit because the delay rate difference is very small. What does a part per million mean? A part per million means that essentially, if I have 1 part per million delay difference, that means that in a million samples, the delay changes by 1 sample. So essentially, the delay rate of change is 1 millionth. And it doesn't have units because it's like seconds divided by seconds, if you think about it. So basically 1 part per million will cause a delayed change of 1 sample every million samples. And because of the way we have chosen the sample rate, it's 1 million samples per second. It means that 1 part per million here will cause a delay change of 1 sample every second of simulation. And we will be able to see that when we use this. So these are the parameters. I'm going to start maybe with the frequency offset because it's easy. So the frequency offset, the only question is what are the units for this? And it says the normalized frequency offset. And it says 0 is no offset. Okay, we already knew that. And 0.25 would be 1/4 of the symbol rate for a digital modem. For something which is more general like this, it's not the symbol rate, which I'm not even going to explain what it is. It's the sample rate. So, for example, 0.25 would be 1/4 of the sample rate, which is 1 megahertz. So 0.25 would be 250 kilohertz frequency offset. Then the calculation we need to do here, but in receiver 2 actually, is what's the name that I gave to this frequency difference? So frequency diff divided by the sample rate. Again, this is supposed to be a fraction. So the value we put in here is supposed to be a fraction of the sample rate. So that is how we calculate it. Then the other thing which is quite easy is how to set the phase difference here in the tabs. I already hinted at that earlier. So we have an exponential, and then we have the phase difference in degrees. I think, where is that? Yes, it's supposed to be in degrees because here is what it says. And the name of the variable is phase difference. So if I'm computing an exponential, the thing needs to be in radians. So I convert from degrees to radians using this numpy function, or you can also divide by 180 and multiply by pi, however you prefer. We get here basically a complex phasor which represents the phase difference between the two receivers. At the moment, it is
And
just, yep.
Sorry, just to know that's
Yeah,
a
yeah.
1J. That's a 1J, right? So this is sort of engineer's notation for an imaginary number.
Yeah, 1J is notation for the imaginary unit. So remember, when we have a complex exponential, the phase we put in here is multiplied by 1J always, because the phase in radians, of course, because that's the way we get the cosine of the phase plus 1J times the sine of the phase. If you forget the 1J, you get a real number, which is just like usually a large number because it's the real exponential. So yeah, very important. 1J, this is the complex unit. Good question. Maybe any other questions so far? I will get to this epsilon thing in a second. Okay, so epsilon, we have in here the delay rate difference in parts per million. And this is supposed to be a quotient. So I'm going to write the formula and I'm going to explain it. It's going to be delay difference rate. I think it's the name of the variable, delay rate diff. So like this. And the reason why this formula is, first, this is in parts per million. So if we want to convert to parts per one, we need to multiply by 10 to the power minus 6, which is in scientific notation represented like this. And then that is basically what we get. 1 plus some small number means apply a delay rate change which is slightly faster than no change. And 1 minus a small number, which would correspond to having a negative delay rate, would mean apply a delay rate change which is slightly slower than no change. So that's basically the reason. It's like the quotient of delays. So that's what you get. Okay, so this is how we set the values. And then something else, I want to connect the two receivers, and just because I have it on my flow graph here, I will show, I don't remember if I showed it already. I think I have this virtual sync. Yeah, I did. This virtual sync and virtual source. So to keep this more tidy, I'm going to create a virtual sync, which is called astro signal. This is my astronomical signal. And then I can have a virtual source for each of the receivers. And then I don't have to have like lines running all over the place, which is convenient. So I also need to type in here astro signal. And these are our receivers. You might have noticed that there's one thing which is missing yet, because here we had 4 different parameters that we want to simulate. But we have only entered 3 of them because there are only 3 fields. And you might be asking yourselves, how about the other one? The other one is the delay. And the reason why we haven't done anything yet is there is no delay in this block, unfortunately. But luckily for us, there is a delay block, which is really simple, that we can use. The only thing that it takes is the delay in samples, the number of samples to delay stream. It says greater or equal than 0. That is actually a lie. It used to be true in previous versions of GNU Radio. Now, and it lies even, it says you cannot initialize this block with a negative delay. Now you can do it. It works. So we should update that documentation at some point. I think this is called delay diff. Yes. So this is how we are going to simulate the delay difference between the two receivers. And now the thing I'm going to do is I'm going to move this over here And I'm going to put 2 inputs because we want to look at the input from both receivers. And maybe let's put some labels. I don't know if I've shown these, maybe not. If you go into config, you can say what's the label of input 1. So that's going to be receiver 1, and then the label of input 2, so receiver 2. And they will have different colors, but in this way, we will be able to tell exactly which one is which. And basically, we can see just the same signal on both receivers. At the moment, the differences I have applied are 0, so there is 0 phase difference, there is 0 frequency difference, there is 0 delay, etc. But the only of these effects that I can see in this spectrum plot is actually a frequency difference, and I would need to set it quite large. Maybe is 1 kilohertz enough? I don't know. Maybe let's try an average to see. You can see this better. Maybe let's try 10 kilohertz. Yeah, so we can see it. If we set a frequency difference which is large enough, we can see, you can look at this more closely, the two things don't match in frequency. This receiver number 2, which is the one that we are applying the delay difference to, has been shifted up by 10 kilohertz, and we can see it moving to the right. So that's like a demonstration that this frequency difference is actually working. However, in real scenarios, the frequency difference between two antennas will be very small. It will be on the order of just a few hertz. So we will not be able to see it on the spectrum because we don't have enough frequency resolution. But nevertheless, it will be important, as we will see. Then the other things we cannot see because phase difference, we cannot see the phase on the spectrum. We are only measuring power. The delay, we cannot see the delay. This is just noise and it looks the same no matter now or 1 second later. So even if we delay the signal on receiver number 2, we will see basically the same thing. We will see noise. But now what we want to do is to combine the signals from the two receivers. And the goal here, or the most immediate goal, is to combine the power which is received by the two receivers. Because you can imagine if we have an astronomical source, the signal is usually going to be pretty weak because the source is very far. And to collect as much signal power as we can, because that's what dictates the signal to noise ratio we get, and then that's what determines whether we can whether we are able to detect the source at all or not, and also if we are doing measurements, how accurate these measurements will be. So basically, the better SNR we get on a source, the better. So then you can imagine if we have larger antennas, we can collect more of that power because we have more collecting area. And another idea we might apply is to have multiple antennas because that amounts to more collecting area if we sum the collecting area of all the antennas. But then what to do, because each of the separate antennas has a separate receiver. Basically here we are simulating two antennas with one receiver each. We want to combine the signals somehow so that the power is combined. And the way to combine the signals is as simple as an addition. So that's the mathematical sum. But the signals we add need to be properly aligned. They need to have the same delay, they need to have the same phase, they need to have the same frequency, etc. Otherwise, we will have some effects that we will see in a second what happens if the signals are not aligned. So basically, what any radio telescope that has multiple antennas does to perform beamforming, that is to combine the signals from all of the antennas so that the power is summed, is to align the signals from those antennas, taking into account those phase differences, those delay differences, etc., etc. And once the signals are all aligned, they can be added. And that is how we essentially combine the power. So you could ask yourselves, how do we apply these? How do we know what corrections to apply? How do we know what is the phase difference, etc.? So some part of these quantities or a contribution to these quantities comes from just where the source is on the sky, where the antennas are located on the ground. That is called geometric delay. We can compute that. Then there is also another contribution of the delay, which is called instrumental delay. You can imagine we might have cables from the antennas to the receivers. Those cables might not be the same lengths, and we will see something like that at the Allen telescope array. They are fiber optics cables, and they are not all the same length. And also the delay on those cables depends on temperature, and it can depend on other things. So we have delays in our instrument that we need to account for. And to do that, there is a way of calibrating using sources on the sky, usually bright enough point-like sources such as quasars, to measure the intrinsic delays that we have on our system. So we can measure them, we can calibrate them out, and then the only delays that we need to take into account are geometric delays because of where the source is located with respect to the antenna. So we will see all of that in action next week at the ATA. I just want to lay out like the basic concepts here. So let's look into how the addition of these signals looks like. To do that, I need a third input, which is going to be called beamforming. So let's set this to high. Let's also do it like this. And now the thing you need to notice is the green is the beamformed combination. If you look at the noise floor to save some time, and because the plot is very busy, I'm not going to make the actual measurements, but you can believe me, the difference between the noise floors in the green line, which is the beamform combination, and the red and blue lines, which are the independent receivers, is 3 decibels. And the reason why it is 3 decibels, we already know. Essentially, we are summing two noise sources which are independent. So the powers add, and we get twice the power, so we get 3 decibels increase. So this has gone up by 3 decibels. However, if you look from here to here, the difference is larger. It is actually 6 decibels. And the reason for that is because the signal is exactly the same on receiver 1 and receiver 2. The noise is not. That is the reason why we have set seed 1 and seed 2. It is different noise. It has the same statistical properties, but it is different. But the signal which is in here, it's exactly the same. I'm just feeding it the same. I'm applying the same numbers. I haven't yet changed any of these fields. So I'm applying the same numbers on the channel model, except for the noise. And so from my astronomical source, I have the same signal. So if I'm adding 2 copies of the same signal, I will have 2 times my original signal. And then that means the amplitude increases by a factor of 2. But because power is amplitude squared, the power is increasing by a factor of 4. And a factor of 4 is 6 decibels. So what has happened here is the noise floor goes up by 3 decibels. The signal of interest goes up by 6 decibels. So the signal to noise ratio, that is the difference between this and this, goes up by 3 decibels. And you can really see it. You can see that this signal to noise ratio is better than the signal to noise ratio. So that's what we expect. Basically, we are combining 2 receivers which have the same antenna characteristics, so they have the same signal to noise ratio, and we expect to get basically like a virtual receiver which has an antenna collecting area which is twice as large. Then we should collect twice as much power from the source, and the signal to noise ratio should be twice as much, and that's an improvement of 3 decibels. And that's essentially why beamforming works. And you could run the same numbers for many antennas, maybe 42 antennas like the Allen telescope array. So if you add 42 antennas together, then I don't know how many 42 is in decibels. I guess it's something like 16 So you would get an increase of 16 decibels of SNR compared to receiving the source on just one signal. So that's how beamforming works when the signals from all the receivers are aligned in phase, in delay, in frequency, in everything. Now we will look at what happens when they are not aligned, but before that, any questions? Okay, so what happens if they are not aligned? Let's look first. I'm basically going to play with all these four numbers to show you what happens. If they are not aligned in phase, then they will not add. So for example, if I set phase difference equals to 90 degrees, we can see that the beamforming combination decreases. I can repeat that again. At 0, that's here. At 90, it drops a little bit. I can increase even further, 120. And if I go to 180 degrees phase difference, that means that the signal phases are opposite. 180 degrees is like putting a minus sign, it's changing the sign of the signal. So now what happens is the signal here is equal to the signal here, but with the opposite sign. And when they are added together, they subtract and we get 0. So we are completely removing the signal of interest. Not great if what we want to do is to observe this source. But there is a situation in which this is useful, which is perhaps we have an interference, and the thing we want to do is to remove that interference. So we can play this trick. We can use the signal from multiple antennas to cancel each other out and remove the interference, often completely, like in this example. And this is called null forming. So that's also interesting. It's a method for interference cancellation. But if the thing we want to do is to get the best signal to noise ratio, because this is our signal of interest, we have seen the phase difference of the antennas needs to be 0. And if it is not, we need to apply an additional phase shift to one of these two signals to correct for the phase shift that we have. That would be done essentially the same way I'm doing the phase shift here. What happens with a frequency difference? A frequency difference is the same as a phase difference change over time. So if I set this to 0.1 hertz, that means 1 revolution every 10 seconds. So we will see that the things add constructively and then add destructively. That means they cancel out and those alternate, and the period is 10 seconds. So I'm going to hit enter and we will see it. Now the phase difference is 180 and they distract. Now it's they combine, and now they combine again destructively. And in radio astronomy, this pattern of combining constructively and then destructively, etc., which depends on the frequency difference, is called fringes. So if you hear about the term fringes in interferometry, this is essentially what it means. If we were looking at the power measurement, we would see that it goes up and down. And the reason for that is because there is this frequency difference. So if we want to do beamforming for the purposes of combining the two signals properly, then we need to have a frequency difference of 0. What happens with the sample with the delay difference? To demonstrate that, because it's easier to see, I'm going to make this wider. I'm going to make it 400, and maybe I'm also going to make it a little bit stronger. It will be easier to see in this way. So let's see, if I set a delay difference of 1, sample, we don't see anything at the moment. We will see, let's set a delay difference of 2, and now we see something strange. So this thing has dropped. If I continue 3, we see like there is a null in here. And so we see some pattern like that. I'm going to continue, and now I will explain what happens. So to explain what happens, I'm going to make this even wider, perhaps even 800. So what happens? Basically, we get constructive interference at some particular frequencies. We get destructive interference at other frequencies. The reason for that is that a delay is equivalent to a phase change which depends on frequency. It depends linearly on frequency. So at this particular frequency, there is a phase change of 0 degrees. Then the phase change increases. Here it will be 180 degrees. Here it will be again 0 degrees or 360. Here is 180 again. Here is 0 again. And because we have four samples means that we do 4 cycles of this delay change across the whole spectrum we have. So if I were to set this to 1,000, we could see the 4 notches. So there is like 1 notch here at the edges, and then 2, 3, 4. Well, I'm actually counting wrongly. So 1, 2, 3, 4. The notches are in here. And actually in here I have constructive interference, but we cannot see that because the noise, the signal I'm using actually drops off. But you can believe me, at the edges we have constructive interference. So it's like this, and then first null, second null, third null, fourth null. So that is what a delay between the signals look like. And again, for the purposes of beamforming, we want to cancel out any delay we might have. And finally, how does a delay rate over time look like? So it's the same concept, just the delay is going to be increasing over time. So if I set this to, I said 1 part per million means the delay is increasing by 1 sample every second. So 0.2, for example, means every 5 seconds we will increase by 1 sample. And we will see that slowly. So at some point we get a single null, then it becomes like 2 nulls, and they are getting closer because we will see a third null appearing at some point. So it is here, and then 4, and so on and so forth, because essentially the relative delay between the two signal sources is changing. So that is how the effect looks like. And I can stop this, but because they have accumulated the delay is like that. It's accumulated. If I wanted to compensate this, I would need to place I don't know what's the right sign. Maybe it's positive. If I play with these numbers and choose the right delay, maybe it's about 8 samples, I can cancel it out. So this gives you a hint about how in real we can cancel out these effects to align the two signals and achieve this beamforming combination properly. So questions?
Just a comment. This might seem a little esoteric until you go up to the ATA next week and see, how the beamformer actually works. But you've already seen beamforming in action with the meeting owl that we have here on the table, in the sense that that's using sound waves essentially to kind of determine which direction the sound is coming from, and then to phase up those signals, and then it points the camera in that direction. It's also something that with the sort of newer generations of Wi-Fi signals, that beamforming is important in terms of improving the signal that you get at your laptop, for example. If you see, if you have an access point at home that has multiple antennas on it, it's basically doing the same thing. So it's steering that, improved signal to noise, combining those signals in your direction.
Yeah, exactly. Any questions or comments? Okay, awesome. So let's continue. I think I'm sharing. Yeah, I am. So as I said, the thing we are going to do now is to see how we can take the signals from these two receivers, and I'm actually going to add things for them. So this is going to be antenna 1, and this is going to be antenna 2. And the question is, let's pretend that this is a calibrator source, and the values we are entering here as part of the simulation correspond to instrumental delays and phases that we have in our receiver. We want to measure those to calibrate the receiver out. So this is basically about how to do calibration. And because there are a bunch of blocks, and this is quite similar to something we did last week, I'm going to copy all of this, and then I'm going to explain what this is. So this is all based in FFTs. It's essentially the same as the way I showed last week to calculate and plot the spectrum of a signal when we have a single receiver. But the only difference really is we have the two receivers. We are doing FFTs again. So remember, I copied an FFT size variable here. We are going to use 256. We don't need it to be any larger for this. So stream to vector, we always needed to use FFTs, then the FFTs themselves. And then the only difference is if I was doing the spectrum of each receiver, I would do complex to magnitude squared in here, and I would have the spectra of each of the two receivers. But the thing I'm going to do is to do the multiply conjugate. And if you think about the complex multiplication of two complex numbers, let's say z times w conjugate, then if you think about that in polar coordinates or in polar notation for complex numbers, the amplitudes are going to multiply. We don't care so much about that, but the phases of the complex numbers I'm going to subtract. And that is what's interesting here, because this multiply conjugate operation is essentially extracting for us the phase differences between the two receivers. And because we have done an FFT, we are doing that in the frequency domain actually. So the thing we have in here is like the phase difference. There's also an amplitude component, but we don't care so much about it. What we care is the phase of this complex number, which is the phase difference of the two receivers versus frequency. And that's quite useful because, as we will realize in a second, all the effects we were playing with before the break can be seen very easily in terms of phase differences versus frequency. So what's running here? I think I'm missing some variables or something like that. This is integrate. It's to integrate multiple FFT outputs. It's basically the same as we had last week. The only difference is now this is of type complex because we have complex numbers rather than power, which is a real number. So I think I'm missing like this t-int variable, which is probably 1 second or something like that. I don't know where I put it. 100 milliseconds, so 0.1 seconds. I just want to have like a reasonable refresh rate on this for demonstration purposes. When we do this for real in the Allen Telescope Array, the integration time for the FFT will be much longer. It can be even minutes. Depends on how much SNR you want to recover, etc., etc. So, okay, now this number is computed, and it turns out that we are adding together 390 FFTs to get 10 results per second. And we are going to do two different things with those FFTs. First, we are interested in the phase of these numbers, because I was saying the phase difference, the phase of these complex numbers is the phase difference of the signals on the receivers. So complex to argument extracts the phase of the complex number in polar coordinates. And then we have the repeat trick. We saw that last week also. And here we have basically the same values we learned how to set up last week. So the number of points is the number of FFT points. Then the x-axis, we get the right frequency values if we start at minus sample rate divided by 2 and have a step of sample rate divided by NFFT. And then because we know that this is going to be a phase in radians, we can set the minimum and maximum values between minus pi and pi. So nothing surprising. This is going to plot the phase, and I have given it a name, which is frequency domain phase. The other thing we are going to do is to compute an inverse FFT. The way an inverse FFT is computed is by setting this thing to reverse. In the forward reverse, we set it reverse direction. It's the same as inverse. And also important, I am setting a rectangular window. I could set it like this as an empty list. These are two square brackets. It's nothing fancy. It's like difficult to see when they are close together, but just an empty list. That means no window or rectangular window. And here, I don't know why I've written window rectangular, but it's basically the same. I could also set it like this. It's actually faster this way because now GNU Radio knows that there is actually no window and it just skips the multiplication by the window. So important, we are doing FFTs with no window. And the reason I want to do an inverse FFT is because I want to go back to the time domain. Remember that we are on the frequency domain. If we do an inverse FFT, we go back to the time domain because this inverse FFT is going to measure the delay between the two signals. Essentially, the way we're doing an FFT, then a complex multiplication by the conjugate, and then an inverse FFT, this is a cross correlation between the signals. This is a way of writing the cross correlation. If you've ever heard about the cross correlation, we can write it with FFTs in this way. And if you're not familiar with the cross correlation, the only thing you need to know is that when we have two copies of the same signal, but they are delayed with respect to one another, we will get a peak, which is called correlation peak, at an x-axis location which corresponds to the delay difference between those signals. So that is the reason why we have this, to see what the delay is, to measure it. The result of the inverse FFT is still a complex number, so we complex the magnitude square the repeat trick, and then this says lag domain. Lag is like a synonym for delay. That's usually how it's called. And that's it. The x-axis is in units of samples, so we have 0 samples and then steps of 1. So these are all the blocks. I'm going to show how they look like. So this is when the signals are at the same phase and frequency and everything. I haven't yet edited any of these. They are all at 0. What we can see in the frequency domain phase is that the phase is close to 0, where we have this signal, and it is completely random. Everywhere else, that makes sense. That is what we expect, because it's actually measuring the phase difference between the two receivers. And in here, the main contributor is the signal, which is the same. So we get a phase difference of 0. In the rest of the spectrum, we only have the noise floor is completely different for the two receivers. So it has a random phase difference. And then in here, we basically get a correlation peak of 0, which because of how the Fourier transform works, it appears in here and here. There's an FFT shift option. I'm going to show it here. So we can play with setting that to yes or no or whatever. And if we set it to no, perhaps it might appear here. So it's just a matter of where to put the center. Here, the center is on both edges of the plot. So this is what a delay of 0 looks like. Any questions so far? Okay, how does a delay of 90 degrees look like? There are all sorts of sign conventions here. Actually, we are like applying the phase to the second receiver, etc. But we can see minus 90 degrees phase difference. So this is how we can measure it. If we had this for real, because I don't know, one of our cables add 90 degrees more phase to the signals from one of the antennas, we could point to a source on the sky, also remove the contributions from geometric delays, and we would be left with something like this, where we can really read the value 90 degrees. The only difference is the actual astronomical noise source is going to occupy the whole spectrum, and we will see the minus 90 degree line occupies everything, just as if I do this. So that's like that, but for the sake of the example, I want to keep things limited to this part of the spectrum. So that's how 90 degrees looks like. 180, it's difficult to see because it's like jumping on the upper edge and the lower edge, but that's what 180 looks like. And we can do 120 or minus 120 or I don't know, any other number we want. Then a frequency difference, no surprise, it's going to be this thing is changing over time. And we can see it's changing, it goes there. And I'm going to stop it when it goes close to 0. So that's it. Again, no surprises. How does a delay look like? I'm going to set a delay of 1 sample. We cannot see much. Maybe I'm going to make this wider. With just one sample of delay, it's not easy to see, but what we should be seeing is a slope on the phase versus frequency. If I make it 2 samples, then maybe I can see it. Maybe I've made a mistake. Yes, I've connected this before the delay, which is a good example. So this thing is not seeing the delay. I should connect it here. So, okay, let's stop it and run it again. I was with, I think, 400, maybe 600. That's what I had. And if I add a delay of 1 sample, I should see it. Yeah, this is the thing I wanted to show. So we can see a slope in phase versus frequency. And it's actually like one whole cycle over the complete frequency range. That's how a delay of 1 sample look like. A delay of 2 samples is 2 revolutions. So it starts at 0, goes here, goes here, goes here. And in total, it has done 2 revolutions. You can see that it crosses 0 total of 2 times, basically here and here. 3 samples minus 2 samples we can also do. So it's the same thing, just negative slope. I don't know, minus 20 samples. There should be like 20 of these across the whole spectrum. So in this way, we can measure delay. And also the whole reason I put the FFT in here is because, again, there is a sign convention at play, but my peak is at 20 samples. If I go to, I don't know, minus 10, now my peak is at minus 10 samples. And if I put 10 here, it goes to the other side. And this all needs to be interpreted with some care regarding signs. So because my FFT size is 256, this number, which is 246, is actually to be interpreted as 246 minus 256, which is minus 10. So sign convention here, but we are basically getting the delay between our 2 signals. And delay rate difference, the same thing. We can observe this moving over time, and we can also observe this signal slowly moving over time. So this is basically how we can measure the relative delays and phases of the signals which are arriving to our telescope. And in this way, we can calibrate out the instrumental effects on our telescope. Any questions about this? Or comments?
Has anybody actually done calibration like in CASA or that kind of thing where you've seen these kind of plots before? If you get kind of into, making images in radio astronomy, you'll be staring at all of these plots or something.
Yep. Yeah, I bet we will also see one of these plots for the ATA where we see all the antennas and we see the phase differences with respect to a reference antenna.
And of course, the point is with the ATA, where you've got multiple antennas, you're pairing up each antenna with a bunch of other antennas. And so then you can often see which antenna is the one that's causing the problem because it appears in sort of a common set of pairs with the other ones.
Yep. Okay, so that's the end of this demo. The second demo I have is where can we go with this? Because so far, the main reason why I introduced beamforming is because we have multiple antennas and we want to combine the power from all of them to increase the signal to noise ratio. But we can do far more interesting things with beamforming, which actually lead in a way or in a sense to making those images that Steve was mentioning. So that's the second demo. and it's a large flow graph, so I'm not going to make it in real time. You can see it's pretty large, and the reason it's pretty large is because it has 6 antennas. It's basically a lot of repetition. So I'm going to switch to the web browser and speak for a moment about what a linear array is. So a linear array of antennas is the most simple kind of array. We have antennas which are equally spaced on a line. This is a diagram from some random paper, and the distance here is denoted by delta. 4 of these, or I don't know, m, it's like a general number, antennas are in the array. In our case, it's 6. I just decided to have 6 in the simulation. The more, the better, but also, the flow graph becomes massive. And then what's the interesting thing in here? The interesting thing in here is that if the source is arriving from this direction to the antennas, then it's going to hit this antenna first. It will hit this antenna next. And the extra travel time is given by this distance, which is delta times the sine of theta. And this theta is like the off boresight angle from the array. So that means that from measuring these phase differences, we can measure the angle of arrival of the source. That's one of the things we can do. Also, if we are thinking about beamforming, it depends on the angle of arrival. So for beamforming, we will need to apply these phases. This is going to get a phase of delta times the sine of theta converted to units of phase. This one actually has twice as much the delay because it's the second antenna. So this will get 2 delta times the sine of theta. This will get 3 delta times the sine of theta, and so on and so forth. So these are the phases that we need to apply to our antennas. And they depend on theta, which is the direction in which we want to look to the source. And the interesting thing about this is that this is all math that happens within a computer. So that means we can do the same math multiple times for different values of theta. We will get multiple results. And that is what that does is it generates virtual beams. It points virtually our antenna array in different directions. So we could be looking at one source, which is in one place of the sky, digitally with some calculations, and then we do some other calculations aside, like in parallel, and we are looking at another source in the sky. So by doing this, we can look at multiple sources in the sky. Only 2 limitations. The first limitation is compute power. Basically, how many calculations can we do in our telescope with our computers or GPUs or FPGAs or any compute that we have there. That is going to limit the number of beams that we can form. And the second one, this depends on the type of antennas we use. In the Allen telescope array, we'll see dish antennas, which are the most common for the higher frequency bands. And dish antennas, they have some limited field of view. So for example, for the higher frequencies and the Allen telescope array, it's like 0.2 degrees on the sky. So that means that it only makes sense to aim these beams within that area of the sky because that's the field of view of individual antennas. So we have like this area, which is 0.2 degrees across in the sky, and we can aim to multiple sources, many sources within that area. That's how a beamformer works. In lower frequencies, it is more likely that we have omnidirectional antennas that can receive signals from any direction in the sky. So that is great because it means that with our receiver, we can basically point anywhere in the sky and we can point to multiple places simultaneously. It's just a matter of compute, and we can make like whole sky images. If any of you is working with LOFAR data or any of the other low frequency arrays, you might be familiar with what I'm talking about. So those are the limitations of beamforming, and what I have here is a demo of the 6-element linear array so that we can see it in action. What do I have? I have 2 astronomical sources, so this is the same thing as before. I have different seeds for these, 100 and 1. I have also different frequencies, 50 kilohertz minus 150 kilohertz, so that we can see them in separate places in the sky, and that will make it much easier for us to distinguish them. But this is for the purposes of this demo or simulation. In real life, many astronomical sources occupy the whole spectrum, and they will not be separated on the spectrum. They can only be separated spatially. That means that because they come from different directions. So yeah, basically our two astronomical signals, astro signal 1, astro signal 2. Then these coming here, they are, this is antenna 1. So they are phase shifted, and the phase shifts I'm applying is 0 times 2 pi times the antenna separation, which we will see in a moment, times the sine of the signal angle. So this is going to be 0, of course. It's silly because it's 0 times something. But you can see if I go to antenna number 2, then I have 1 times the same quantity. Antenna 3 has a 2 times the same quantity, and the quantity is just this delta sine of theta that appeared on the diagram. So this one gets 0 phase shift, this one gets delta sine of theta, 2 delta sine of theta, 3 delta sine of theta. So that's the thing I'm doing. I'm simulating the phase difference that happens because of the location on the sky of this astronomical source. And in this simulation, it's going to be very simple. The sky is one dimension. So it's basically like in here. We only care about this angle of arrival. The same happens for the astronomical signal too. The only difference is we have a different variable for the angle. So this is the angle of the second astronomical signal. So the two signals arrive with different phase shifts to each of the antennas because of their location in the sky. Then each of the antennas has a different noise Gaussian source, so different seed, 1 to 3, etc. Simulating again the noise in the receivers. Everything gets added. And now we need to have our beamformers. So I'm going to have only 2 beamformers, but we can have any number of them. Each of the beamformers works in the same way. We are basically applying phase shifts, which are intended to cancel out the phase shifts, which are naturally present in the arriving signals. So in here, minus sign multiplied by 0, maybe make this bigger, times 2 pi times the antenna separation times the sine of the beamforming angle. So when we want to point the beamformer to this astronomical source, we will make the beamformer angle the same as the astronomical source, and that is the way we point our beamformer to that location in the sky. And this one is the same. It just has a beamformer angle too, because it's the second beamformer. And in here, more of the same. So -1 beamforming angle, -1 beamforming angle 2, and you can believe me, this one has a -2, and the rest of the antennas is the same. Maybe let's show the last one. So -4, why is that -4? It should be -6, I think. Sorry, -5. Yeah, so that's good to know. This is like a copy and paste typo. If only one antenna is wrong, it doesn't matter so much. It only degrades the thing by 1/6, but good to know. Maybe it's also wrong in here. Yeah, it is. So it was like a bug that didn't show up because it was wrong in both places. So yeah, good that I checked. This needs to be a number 5 in there. Once we apply all these phase shifts for each of the beamformers, we add all the 6 signals. So for example, this is the first beamformer. We are adding the signals, maybe zoom out so that you get like the idea of the whole picture, even if it's very difficult to see. Yeah, I don't know how to show this better, but you can see like these 6 tiny receivers, and all of them are added into this large add block, which is in here. And then finally, we show the 2 results of the beamformers on a frequency sync. So we are showing the spectrum. Before I run this demo, any questions? Maybe I'm going to disable these for a second so that I can get back to it and it looks more surprising. So we have the two signals. I believe that by the way things are placed, this is actually signal 1 and this is signal 2. Let's look at the numbers. So the signal 2 bandwidth is 200 kilohertz and it's at minus 150 kilohertz. So yeah, this is signal 2. And this at 50 kilohertz offset and bandwidth 100 kilohertz is signal 1. I also have like different SNRs on them, no particular reason. Currently, they are both coming from an angle of 0 degrees, so they are on the same place in the sky, and we are pointing our two beamformers to the same location in the sky. So the first thing I want to show is that by making this number increase, maybe I'm going too slowly, maybe I should do like, I don't know, 0.05 degrees. So for example, 0.05 degrees, I already get some signal reduction on the second beamformer, which is the red line. We are pointing our beamformer slightly away from the direction that the signal is coming from, and so we see some signal reduction. If I keep going, and maybe that's going too far, so let's do this slowly. So 0.06 degrees, 0.07. You can see the signal is dropping, 0.08, 0.09, and then basically 0.1, the signal completely disappears. So now I'm pointing away from the source. I'm pointing to a different location. I cannot see it anymore. We will see how this looks like depending on the angle. That's the thing I have disabled, and I will come back to it. But why is this useful? Well, let's actually pretend that this second signal source is coming from an angle of 0.1. Then on my beamformer number 1, I only see this signal 1. On my beamformer number 2, I only see this signal 1, this signal 2, sorry. And here it's pretty clear how to separate the two signals anyway, because they are in separate parts of the spectrum. But I could just place them on top of each other if I wanted to. And for example, maybe let's even make them the same bandwidth. So we could have like these two signals, and if they were coming from the same direction, it would be impossible to distinguish them. If we didn't have a beamformer, it would also be impossible to distinguish them. We would just see both of them arriving to our antennas. Because we have a beamformer and because they are coming from different directions, we can point each of the beamformers to each of the signals, and each of the signals will only appear in one of the beamformer outputs. So this is something which is quite interesting about beamforming. We can point these beams to just one particular location. Coming back to what Steve was mentioning about your home Wi-Fi, it has all these antennas, and one of the reasons why it has all of these antennas is because it can point beams, and it can point to, I don't know, your cell phone or your computer, and it can talk to the same devices at the same time because it's pointing narrow beams to each of them. And in this way, it can talk to the same on the same frequency without getting interference, clashing. It's separating them on different beams. So that's how modern communications work. We use beams, and we use space to separate different signals also, not only frequency. Okay, so something interesting that happens is that if I keep increasing this, let's go 120, and this is the red thing. Don't forget, 140. Then it begins dropping down, and this is not unexpected because I'm pointing away from the source. I'm basically pointing too far. 160, 180, and then this would be 0.2 degrees. It has disappeared, but let me continue. 220, 240, 250, 260. You can see it's slightly coming back, and 280. And if I set the right numbers, it will actually come back. And there's a reason for that. It basically depends on the antenna pattern of the beamformer. So that is the thing I'm going to show next. But before that, maybe any questions?
It's another comment. For those of you who are doing single dish SETI experiments or FRB or pulsar detection or whatever, right? You physically move the telescope and nod it on and off the source, and then you compare the signals that you get when you point it in one direction with the signal that you get when you point it in the other direction. And here with the beamforming, you can look in both directions simultaneously and compare those two signals, so you don't have this kind of degeneracy in terms of, is this something that's changing in time, or is it something that is really spatially localized on the sky? So that's why beamforming is really powerful, in addition to what Daniel's saying, that you could do multiple experiments at the same time. So, a primary user can be looking at a pulsar over here, and you can be doing a SETI experiment on some different target and comparing those signals just by combining the signals sort of cleverly using your back-end compute.
Yeah, also something useful about beamforming is that even if you are not using multiple beams, it changes instantaneously because it's only changing some numbers in the computer. Whereas dishes, if they are large, they take a while to move. So that's also useful in some applications where you need to track an object really fast or something like that. You can essentially, the term is electronically steered array. And you can imagine why it's called like that. And it steers very fast because it's all like numbers on a computer. So, okay, I want to plot the antenna pattern of this beamformer. And that's basically like asking, what would I see if I were to have a signal at each of these angles? So how does the response, I fix one angle that I'm pointing the beamformer to, and then based on the angle of the signal source, what is the amplitude that I get on the beamformer output? And that is the calculation I have here. It's just some math I'm going to show you so that you can see that it's nothing too complicated. It looks long because I need to type it in just one line in GNU Radio, but it's basically, so these are like the phase terms that we have on each of the antennas. We have a for loop to go through the number of antennas. So this is essentially what you have seen on the flow graph. It is 1j times the number of the antenna times 2 pi times the antenna separation times, and then we have the difference of the signs, and one is the direction from which the source is coming, and this is going to be an array which sweeps a range of directions so that we can plot something depending on direction. And then this is the fixed beamforming angle that we have selected. So that would be like the quantity, like the phase we get at each of the antennas after the phase compensation that is applied by this beamforming angle. And then we are summing all the antennas. So that's what this sum is all about. And finally, I normalize by the number of antennas. When we sum things, we can either keep the sum or just, like take an average, which is divide by number of antennas. And finally, I'm using 20 times the logarithm of 10 because I want to plot things in decibels. And this is amplitude. So with amplitude, we should use a 20 in front of the logarithm. So that's the calculation, and this antenna pattern in degrees is just linear spacing between -3 degrees and 3 degrees, and we can change that to change the range of the plot, but nothing mysterious. I could do this in NumPy or whatever. I just prefer to do it as part of the GNU Radio flow graph. And what I have in here is just a vector source. We will explain that in more detail in another session. It's just repeating this vector of numbers all the time, and I'm plotting them all the time in a vector sync. So this is how it looks like with the beamformers both pointed to 0 degrees. We get the same on both of them. I'm going to point this to 0.1, for example. And then what can we see here? So let's look at the blue line, which is beamformer 1, which is pointing to 0. This is the main lobe of the beamformer. So if we point, if the source is in the direction we point, we get 0 dBs. Basically, that means we get maximum signal. As the source moves slightly away from the direction we are pointing, then the amplitude decreases until it hits a minimum. And that minimum is about at 0.1 degrees. So that's here. That's something we saw before. If I keep increasing the distance to the source, then this thing comes back up. And then it comes back down, it comes back up. And eventually, and that is the thing I wanted to show, and I didn't find the right value to show it properly, we still get a full response. So something important about this particular array is that whenever we point to 0 degrees, we are also pointing to something like 0.57 degrees. Maybe 0.57 degrees is already outside of our primary antenna field of view. For example, that would be the case with the Allen telescope array antennas at high frequencies. The antennas, they will always see like this part of the directions, and these would be greatly attenuated by basically by the dish antenna pattern. But if we have omnidirectional antennas, we will also see this direction. So these are called grating lobes, and depending on the beamformer design, we can either have grating lobes or we cannot. I think I have enough time to explain exactly when grating lobes happen. But the thing you need to know is that these are like a factor of nuisance. We don't want these. Essentially because they mean we are pointing here to the intended direction, but we are also receiving signals from wrong directions. But there are ways to deal with them. So this is our antenna pattern, and this is just the same shifted 0.1 degrees. The thing I want to demonstrate just by looking at the antenna pattern, we could repeat the same thing experimentally by placing these signals in the right places and verifying that actually this thing matches what we see here, but I'm not going to do that, is how does the antenna separation affect the antenna pattern. So far, I have glossed over the antenna separation. I have a variable here, which is the antenna separation, and it says that it's in wavelength units. So before, for example, I was saying 1 gigahertz has a wavelength of 30 centimeters. So if my antenna separation is 100, then that means that my antenna separation is 30 meters. So that would be this delta is 30 meters, and then this other one is 30 meters away and 30 meters away, and so on. And if I have this 100 wavelength separation, then my beam pattern looks like that. And what happens if we, I don't know, cut this by a factor of 10? Maybe that's too much. Let me try 20. Yeah, perhaps better than 20. Maybe let's do 40. So you can see everything is basically larger. Now the first null is not at 0.1 degrees, it's at 0.25. And this one is farther away, and the other one is farther away, and so on and so forth. So if I have the antennas quite close together, I'm going to demonstrate that for the sake of the example, although no one really does that in radio astronomy, like half of a wavelength, that's got to be small antennas. They cannot be dishes because dishes are usually multiple wavelengths in size. Otherwise, they are not useful as dishes. But just so you know what happens, where is my thing? So I think I can go from minus 180 to 180 here to give you the full picture. Yeah, so basically in here I get essentially no grating lobes. I don't have a way of distinguishing between signals coming in from the front or from the back, which is minus 180 degrees. And that's built into the design because here, I mean, if the signal is coming from the up direction, which is the front, or from the down direction, the array looks the same. But this is the way of having no grating lobes. Basically, putting the antennas half a wavelength apart or less. No one does that in radio astronomy. It's not practical. They can do that in your Wi-Fi router, for example. And if we put more and more antennas, we will have a narrower beam. The width of the beam is defined by the longest baseline that we have. So that for this kind of array depends essentially on the number of antennas, on the separation between antennas. Yeah, so what else? Let me set this back to 100. This plot was only limited to a plus minus 3-degree field of view. And this is what we get. So grading lobes, grading lobes. If we increase this to 1,000, maybe 1,000 is too much, maybe 300, we get narrower beams. So it means we get better angular resolution, but we also get grading lobes which are closer together. So that is like the trade-off. In all these cases, we only have 6 antennas. If we kept adding more antennas, we could decrease the width of the synthetic beam. That is how this is called, without decreasing the grading lobe separation. Questions maybe or comments?
Yeah, I have a question.
Yeah,
So
good.
if I have like an observation going and I have like a signal, like how do I know which grading lobe my signal is actually coming into?
It's not possible to know it without other information, because essentially what happens is these gradient lobes happen because you have this exactly the same phases of arrival on all of the gradient lobes. So
Yeah.
you wouldn't have enough information on your array to tell the direction in which the signal is coming from. You would either need to change the location of your antennas, and I will get back to that in a second, because it seems crazy. Well, the VLA does it, but for slightly different reasons. But yeah, if you change, like physically change the direction of your antennas, then you can imagine by the changes I've been making, the grading lobes will be in different places. So you would be able to tell if the signal is coming from the intended direction or a grading lobe. So that's one way to do it. Um, Maybe also frequency. If your these depend on frequency. So if your signal happens over a very wide range of frequencies, maybe you can also tell it apart. But that's pretty much it. The other way is that grading lobe candidate actually within the field of view of your dish? If you have a dish antenna, maybe only some of the grading lobes are within the field of view. Any other questions?
Just to sort of add to that answer, maybe you're getting to this, Daniel, but you go to the ATA and it's not 6 dishes in a line. They're spaced out in what looks like a random pattern initially, but the idea is basically that you get a lot of information on the different spatial scales, and then you can localize things in the sky.
Yeah, exactly. Here, the gradient lobes are like very regular, and that means very bad because it's a very irregular array. It's a linear array. If you spread dishes randomly, then you get like all these random distances, which means random phases, and you still get some gradient lobes, but they are much smaller. So that's what happens for real telescopes. There are some telescopes which are linear arrays, but more of them are not because there are other antenna placements which make more sense. So finally, the final comment I wanted to make is, what does this thing have to do with imaging? You might have seen these radio frequency images made of astronomical objects. And you could imagine the way we can build up to those images with this beamformer, because you could imagine if this is really narrow, we can keep changing these numbers and like make measurements of what's the power coming in from each direction. Each of these directions would be like a pixel that we have in our image. And basically we are scanning all the pixels. And in this way, we form an image of what's the power that we receive from each of these pixels in the sky. That is a very poor way of doing it, because essentially it means that you need to go through all of those pixels, and the number of pixels is like the size of your image to the power 2. But you can see here there are lots of exponentials. There are, for example, in this formula, there is the exponential of 1j k, very important, times 2 pi, something, something. Maybe this reminds you of the Fourier transform, which has something which is very similar to this. And in fact, there is a way to perform all these calculations by doing Fourier transforms. And that is essentially what imaging does, or the way that imaging is normally implemented. It's not built out in the naive way, which would be we have a beamformer and we sweep it over all the pixels in the sky. It's done more in this way. We generate these correlations, which are called visibilities, and then the Fourier transform of those correlations with respect, not with respect to frequency, which is what we have done here, but with respect to space, or with respect to the baseline location, will give us the image of the object on the sky. And you can think about this, and it's actually the case, as just a mathematical trick to leverage the power of the Fourier transform to do the calculations more efficient. It's not only that. I don't want to oversimplify it. There are many reasons why it's important to understand interferometric imaging the right way. Like, we have these visibilities, and so they are on the visibility plane, and we make the Fourier transform, and we go to the sky plane where we have the image. So that's the proper way of understanding it. But at an initial approximation, you can think about it's like this demo. We are just doing a whole bunch of FTs to make all the pixels as ones, essentially. So that's one of the things I wanted to say. The other one is I mentioned physically moving your antenna so that the grating lobes are in different places. And there's a way to do that indirectly, which is that the Earth moves, or the apparent location of the source on the sky moves. And what that means is that the baseline that the object is seeing keeps changing. You can see that if this object is like moving over here, then the angle will change. Then these distances will keep changing. And that means essentially that over time, I'm using different baselines. So over time, as I observe the source, these grating lobes will not coincide. I will get more measurements, which are useful for my imaging. And essentially, there's an analogy which Steve makes, and I think it's a great analogy, which is if you have a very large single dish, you can get very good images because you just sweep your dish all over the sky and you basically scan your pixels. And then you can imagine if you are punching holes on the dish, essentially you get this weirder antenna pattern which has some grating lobes, and so your images are not so nice. And this interferometric image is essentially what happens if you keep punching holes on your large dish and you are only left with your individual small dishes. The resolution you are going to get is the same as the one of the large dish, basically the longest baseline between your small dishes. But you are going to get these artifacts from essentially having too many holes into your virtual dish, which are partially filled out as the Earth rotates, but not completely. And so there are algorithms to clean all this data, and it's actually called the clean algorithm. Like, the basic algorithm for imaging is called clean. So that's it. I don't know how much of imaging we will see in the ATA. At least there are some cool posters. So now you have some insight about how those posters and images are made.